That's why there's no recording for last classes. I forgot to record. Nobody caught me. Okay. So this is lab 2, week 3. As you've learned, the last activity takes a little bit more math. Don't expect to finish lab 2, week 3 in lab next week, because lab 3 it's a 1-week lab, and it will take you the whole hour or the whole time allotted. It's MATLAB. And it's something a little bit different. I've simplified the lab considerably. This was actually based on another professor who's no longer here, homework problem for 325, and it turned into a 2.5-hour lab for 280. The first part, we're going to be doing partial fraction expansion using MATLAB. Fairly straightforward unless you have complex terms, and then you have to do a little bit of and then the second part is solving differential equations using Laplace transforms and MATLAB. You go through step by step and follow the directions. That's pretty much it. There's a lot of cut and paste. I think I took the second part out because that was the one that was making people cry, including me, because every time they upgraded MATLAB, the lab wouldn't work anymore. It's one of those things where MATLAB doesn't like its own syntax, and I couldn't figure out, and so I just finally said, if I can't do this, then the students can't do it. Okay, the only MATLAB programming I know how to do is what's in these labs, by the way. I learned what I needed to get through them. Lab 3 is going to be, okay, so that should say 2. Wait. That should say lab 2. I don't know what I'm thinking. Homework 5 is due on Monday. Exam 1, Monday or Wednesday based upon your last name. Tuesday, if you're doing it online. I think I've got everyone scheduled for that already. If you need to get scheduled, send me an email soon, so I'm not all flipped out. And I'd like to plan ahead. Lab 4. I decided what I'm doing with spring break. I'm going to call it pseudo spring break. We will have class. There's no lab on the schedule, so there's no lab that week. There's no homework due that week, and there's no pre-lecture quizzes due that week. But I'm going to have class, and then that way I can maybe actually cover the electronics part of this class a little bit better, in a little bit more detail, because I've been feeling rushed the past couple of semesters. So that is what is pseudo spring break. Less work, more time, and I'm just going to have class. That's it. Exam 1, you get 2 sheets of notes. You can copy those key slides into them. You just have to shrink them down so they fit on your 2 sheets of notes. I'm not going to give you Laplace transform tables on the exam, but you will have to do Laplace transforms. So I really highly recommend just copying those tables. If you make them like a quarter of a sheet, you should be able to fit all of those tables on one sheet, and then another sheet for notes and formulas and things that you need. It's a really good part of your study to make this note sheet yourself. I've seen people just copy other people's note sheets, and then they don't know where things are on them, and they haven't learned anything by putting the information on there, and so they tend to do really badly on the exam. Writing the stuff down and condensing it into one piece of paper is a great exercise for learning it. Go through those homeworks, think about what formulas did you need to do the homeworks, those kind of things. What information would you need now to solve those problems? Shorter than the homework problems, because I'm only expecting you to, the first time you see them, and you get like 10 minutes a piece to do them. So I'm not going to make them really hard problems. I'm going to make them shorter problems. Yeah, we're watching Asterix the Gaul on Monday at 5:30. You can either come in through Zoom, or we'll be in the cave or one of the other rooms with a note on the door. So that should be fun. We're talking about doing a soldering workshop, but it would be a reservation only soldering workshop. Last soldering workshop we did, we had 65 people in EGR 237, and I have a feeling someone will get upset with that. So what we're going to do is like maybe limit it to 10 people and spread it over 3 rooms, and have the peanut gallery coming through, the people, the usual IEEE people coming in and helping out. Soldering's a really good skill to have. You'll need to do it at least once in your life if you're an electrical engineer. Frequency response, we want to get through these Bode plots. We'll start talking somewhat about this today. As far as, I'm going to give you the cookbook version of what the solution for this is. We'll look at the frequency response plot, and we'll actually be able to write a transfer function just from looking at the frequency response plot. This is something engineers do a lot. I call it my test equipment. I get my oscilloscope, I put it in fast Fourier transform mode. It gives me a frequency response plot. And what I can do from that is I can like guess what the transfer function is, which helps me, because once I get a model of the transfer function for that circuit, I can model things like stability. I can put it into MATLAB and put all these weird edge cases on it and see if it will work under conditions, worst case conditions. This is what we've been talking about. This is where we've gotten so far. We've looked at the Bode plots of individual factors. So we've looked at a constant. We found it is a constant. If I take 20 times the log of the constant, I get, I know you can't read this, but there's another version on BB-Learn. 20 times the log of a constant gives me the magnitude graph, and the phase shift is 0. If I get a factor, if my H of S has a K out front, that would be my constant. If I have an S in the numerator, that would be a 0 at the origin. And it has a plot that looks like this. It passes through 1 radian per second at 0 dB. Somebody talking to me? Okay, at 0 dB, and has a slope of 20 dB per decade, and has a positive phase shift of 90 degrees. A simple 0 is just an S in the denominator. It does the exact opposite. It still passes through 0 dB at omega equals 1, but the slope is down going, and the phase shift is minus 90 degrees. The simple 0 looks like 1 plus S over omega naught in the denominator. And it is going to be plotted. It's 0 dB until I get to omega naught, and then it starts going up at 20 dB per decade. And the phase shift is 90 degrees, takes 2 decades to get there, starts at omega naught over 10, finishes at 10 omega naught, and has a slope of 45 per decade, 45 degrees per decade. Simple pole is just the upside down version of this. 1 plus S over omega naught, maybe different numbers so these don't cancel out. It stays constant until I get to omega naught, down slopes at 20 dB per decade, and has a negative 90 degree phase shift with the same type of graph. What we're going to do today is we're going to look at how we plot quadratic zeros and poles, and then we're going to use this. If I have an arbitrary transfer function, how do I draw the plot of that? And then we'll talk a little bit about filters and some applications of this. The filter lab is lab 4. It's not as bad as the defibrillator math. That was what you're actually building today in lab, was a defibrillator. And when Sharber was here, before our shop manager retired, John Sharber, he had been here since like the 70s. Okay, this kind of grouchy old guy, but he kind of knew how to build anything and was really patient with the students, helping them out. But I would say things to him like, well, what are you doing? He'd say, what are you doing in class today? We're building the defibrillator in the 280 lab. And I would send students off to him and tell them that they wanted to build a defibrillator just to watch him blow up. I'd often sometimes send students to him asking for a negative resistor. I miss him. Okay, so this is the standard form for these quadratics. This is a quadratic 0, and it's a big mess. We have a 1 by itself. We have 2j. Omega's our variable because it's h of omega. I've got the snake thingy here. It's actually a lowercase zeta, but it looks like a snake, and that's what it does. And I have a pole frequency or 0 frequency, which is my omega n. And it shows up twice in the standard form. So in order to plot these, I've got to put the equation in the standard form first. And you'll have to do this in the lab, like somewhere in lab 4. So the first thing I do is I look at this equation and I see I've got a 25 instead of a 1. So I want to factor out that 25 to try to get it towards standard form. So this is J 12 omega over 25. And this is minus omega squared over 25. Okay, it's closer. Now this last term, remember, was j omega over omega n squared. J omega squared, j squared is -1, so I can make this plus j, and when I square that, I'll get the negative sign back. Omega, and then the square root of 25 is 5, and then square it. I always do that last term first, because you'll see why in a minute. 25 times 1. Okay, this one right here, from the last term, the j omega over 5 squared, I know what omega n is. My omega n is 5. So when I'm looking at that middle term, I'm going to want to have a 5 in the denominator. So if I put 5 in the denominator here, it's the same thing as dividing the numerator by 5. So I want to get this in the same form. 5. I had an omega. I had a j. I need a 2 out front. So I'm going to divide the 12 by 2 and make it 6. So 2 times 6 is 12. So that's telling me the only thing I have left that's not in standard form that doesn't quite fit is the snake. So my snake equals 1.2. Now, if we want to plot this, this is simpler to plot than you think. We already know how. It's a 0, it's a quadratic 0, and I'm going to revert, and you'll hear me using these terms interchangeably. This is like a double 0. Our Bode plot approximation is to plot this like there's 2 zeros at our omega n. And in this case, our omega n is 5. So my magnitude plot, I go up to my omega n. It's going to be, and this is magnitude, and dB. And I'm going to switch to bamboo paper. I've already got this planned. When we do real plots. This is 0 dB. It stays there until I get to omega n, and then it starts going up. Instead of 20 dB per decade, it goes up 40 dB per decade. So it should hit 40 dB at 10 omega n. It's just like plotting 2 zeros at the same frequency. The same thing happens with the phase shift. It's 2 zeros at the same frequency. So instead of going between 0, oh good, it's too quiet. Multiply J. Yeah, to get the last term on there, if you've got J in the parentheses and the whole parentheses is squared. So J squared is -1. So that J actually would fall out and make, if I multiplied that out, I would get -1 omega squared over 25. If I actually did the square right. How did I get 40 dB? A quadratic zero is like a double zero. It's like having 2 zeros at the same frequency. So if I had 2 zeros at the same frequency, each one of them would go up 20 dB per decade. And if I add those two graphs together, I'm going to get 40 dB. That will become more clear, I think, maybe after I start doing some examples. We're going to start adding these together. Was an omega squared. If it was plus omega squared, oh, that makes it hard. If it was plus omega squared, I would still need the J in there. I would still need the J in there. And this would be, I think this would become a minus. And then that would not be right. Because that would imply a negative frequency. And negative frequency does not happen in the real world. So it's not, mathematically you can do that, but engineerically you can't, because it's a non-real situation. And I'm telling you this when I'm talking about imaginary numbers. Yeah, it would be really hard to have to do, and it's not going to happen. Yeah. Okay. So my double zero, my quadratic zero, it's going to double the phase shift because I have 2 of them. And so it's going to go all the way up to 180 degrees instead of, 90 degrees. This is omega n. This is 0.1 omega n and 10 omega n. And the rule is that the way it looks like the actual graph, if you actually do the calculations, is it's 0 until I get to 1/10 of omega naught, and then it goes to 180 at 10 omega naught, and it's linear in between. So the slope on this, instead of being 45 degrees per decade, is 90 degrees per decade. It's just a double zero. And if we go back, do I really want to do that to you guys? Go back here. Oh, no, not that one. Must be, where did I put it? Ah, right there. And if we go back to this one, it shows you that this is 40. The slope is 40. It goes up to 180 degrees. And it's the same thing as if I plot one of these have a little power on there. If I have the same pole squared, then the slope is 20 times that power. That says 20n. And the final value is 90 times n. If you look at the chart in BB Learn in detail, you can see all those numbers written on there. That came out of another textbook. Oh, did I really do this? Yeah, I did this. Okay, we plot these. And we plot them with something, I'm really sorry about that graph, but that's the only way I can make it look semi-right. I know it's upside down and inverted, but it's the right shape. Our Bode plot approximation is to do this: 0 dB until I get to omega naught, and then I get this upgoing slope of +40 dB per decade. The snake, this thing right here, oh no. Slide 9, I'll be back.